All right, in this example, we're looking at how many molecules are in a container. So imagine you have some container, like with molecules that are moving around. Maybe we give you the volume, the temperature, the pressure, and we have to figure out how many molecules there are. So how do we solve that? So let's go back over here. Let's write down what we know. All right, we have a volume of 100 centimeters cubed. We have a temperature that is in 20 degrees Celsius, and we have a pressure that is 100 pascals. All right, and what we're trying to find in part A is the number of moles in the container. In part B, we're trying to find the number of molecules. Everything looks okay, but I should point out that if you look at it, the volume here is not in the right units. Remember, we want our volume in meters cubed. And also, we see that the temperature is in Celsius, so we need to convert that to Kelvin. So that's going to be 20 plus 273 in Kelvin, so this gives you 293 Kelvin. And then let's do the conversion to centimeters. All right, so remember that in 1 meter, there are 100 centimeters, but we're going to go 1 meter by 1 meter by 1 meter. So that's really, we're going to cube that. So really, it's 100 divided by 100 times 100 times 100. So if you think of it as you have 10 to the power 2 in centimeters cubed, and on the bottom, right, you have 1 million centimeters cubed. So 10 to the power 2 divided by 10 to the power 6, all right, is going to give you 1 times 10 to the power negative 4 meters cubed. Okay, now we're moving on to using the ideal gas law. We also remember that R is 8.31 joules per mole Kelvin. Okay, so we can move on to solving this. Okay, we're going to use the ideal gas law, PV equals nRT. So the number of moles would be equal to pressure times volume divided by gas constant times temperature. Okay, so let's plug in here. We're going to have, let's get back in there. The pressure is 100 pascals. The volume is 1 to the power of negative 4 meters cubed. The gas constant is 8.31 joules per mole Kelvin. And the temperature is 293 Kelvin. Okay, so that gives you an answer of N equals 4.107 or 11 to the power of negative 6 moles. Okay, for part B, there's a number of approaches that you can use. You do know that Avogadro's number is 6.02 times 10 to the power 23 per mole. So you could use that because this is going to tell you how many molecules you are. So if you want to find the number of molecules, you can simply, let's see here, we'll write Avogadro's number, 6.02 times 10 to the power 23 atoms, let's say, per mole, and then multiply by how many moles we have, which is 4.11 to the power of negative 6. I'm barely fitting that in there. So that gives you 2.47 to the power of 18. And I wrote atoms, but actually it should have been, molecules, because we were dealing with molecules in this case instead of atoms. But anyway, you could, just to point this out, you could use PV equals N times the Boltzmann constant times the temperature T, right? That's the other version of our ideal gas law. You know the pressure must be in pascals. The volume, again, must be in meters cubed, right? Temperature in Kelvin. And Boltzmann constant is 1.38 to the power negative 38, I think. Or negative 23. Okay, and then you can solve it that way as well. Okay, and that's it for this example.